Hey, welcome back. This is actually the last episode on this sort of thermofluids book club. It's been like 29 or 30 episodes, something like that. So we're going to wrap it up today. We're going to wrap it up both by finishing here in Panton and then back to statistical mechanics and sort of the highlights for you to go read. Again, I'm framing this as an engineer. If you're a physicist, you're absolutely going to go take statistical mechanics for real from a good graduate class. And so we're going to start here, chapter 25. This is actually all about stability and transition. So we've already talked about turbulence. I did that earlier. And so really the interesting point here about stability and transition, and I showed some fun videos last time, kind of like the Taylor-Couette flow, and you see these things. But we actually have a few things that we can actually analyze analytically from a stability and transition point of view. And so what you end up doing is you say my velocity field is some sort of mean flow plus some fluctuating flow. This could be the same that you would see in turbulence when you're sort of splitting the flow between mean and fluctuating. But really what we're doing here, and we'll of course say that U prime is much, much smaller than U, but we're going to basically take an expansion on this. And so in a channel flow, and this is one of the more fun ones, in a channel flow, you can actually take, and you can assume a form on the fluctuating component, which is, writing it down, some function of y, and then there'll be an exponential that's going to carry a couple interesting pieces of information. This is alpha x plus beta z minus alpha ct. Okay, and so c is the part here that we're going to take a look at, because c is going to have some real component plus imaginary number times I. Sort of an imaginary component. Now, because this was an exponential and there was an I already here, which means from any real components here is going to be a wave, which is okay. It's actually this I component here, sitting here, that's going to be a thing that blows up in time. And so we're actually looking for here is we're going to solve for the fluctuations that blow up in time. Okay? And so you can take a look at, we talked about the Kelvin-Helmholtz last time. Helmholtz. By the way, this is what you hear when you're in your car and you open up your car windows, like in the back seat. You hear that like boom, 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 fluctuating on your ears. It's actually a slug of air that's kind of going in and out, because the car that's because you're driving fast, you have the air outside the car that's going fast from if you're from the inside the car point of view, and so you're actually getting that shear layer, and the shear layer is growing, and there's the fluctuations that and pop in and out with it. Okay. And so you can actually solve that. Again, this would be, a higher speed velocity on top of a lower speed velocity, right? Where this is sort of, usually it's U2, U1. And so the ith component here of C is actually plus or minus the difference between those velocities. So you can solve for that, right? And so actually the greater the velocity difference, the larger this is, the faster you hit that instability, okay? Now, viscosity will stabilize some of those wavelengths for sure, but for the most part, this is an invested point of view. Okay, and then the other one that kind of goes from that with the channel flow is actually the Orr-Sommerfeld. So I'll write that here. And this is where you have a channel. Now, this only works in channel flow. So where you might look at this and say, hey, that's laminar flow in a pipe. Like, no, this is actually channel flow. So two infinite plates with a pressure difference driving. Now, in that situation, because you have periodic boundary conditions, you can actually solve for this one particularly. And I'll just write it down. But look at, take a look in the book. And so you have U minus C, and then second derivative of the potential respect to y squared minus alpha squared phi minus phi second derivative of the mean flow respect to y squared, and that's equal to 1 over I alpha Reynolds, and then it's the second derivative respect to y squared minus alpha squared and octave phi squared. Okay. So you can look at the derivation of this equation, but Panton does a pretty good job of sort of deriving it. The key point here is, boy, that was pretty messy of me. Well, I was never the cleanest handwriting person. But the key point here is that you can actually solve this. So this is a differential equation. You can go solve it on a computer, okay? And so what you end up getting is this. And you can do it for different pressure gradients as well. And so you have these wavelengths, and so you end up creating, effectively this critical Reynolds number, where based on, and this is on boundary layer theory, it's the same, you can do the same sort of thing, but where you have sort of unstable critical Reynolds numbers, and if there's an adverse pressure gradient, it actually becomes less. So, right, adverse pressure gradients, that's where you have separation over an airfoil, and so you would have these instabilities show up a little bit earlier. Okay, and the first one is really to solve this, or Tolman and Schlichting, and so that's actually Tolman and Schlichting, TS, and so it's actually that first instability we actually call the Tolman-Schlichting waves. And so I think that should be the next picture here. Yeah, so here's your boundary layer. And so you might have like, pure laminar, and then all of a sudden at this critical Reynolds number, you then see these Tolman-Schlichting waves, which is the solution to this. And they just kind of look like these sinusoidal waves, but then they actually break down into the third dimension. So now you get things going in the third dimension, and then you eventually get turbulent spots, and then the turbulent spots then pour into three-dimensional turbulence. Now, when I was getting my master's degree at UT Austin, actually my friend who ended up forming Excess Engineering, my first company with me, at UV, we were hired to redo the fluids lab. And we actually created, it is in a pipe flow, we created this beautiful experiment in pipe flow, a clear plastic, we had it laminar, and you had blue dye going in there. You could actually see, as you turned up the flow, you could see the blue dye going from straight to a couple waves, which is the Tolman-Schlichting waves. And then those waves would start corkscrewing, which is this region 2 here, where you're getting that three-dimensional nature. And then you would turn up the flow rate a little bit more, and you would get the turbulent spots, and then boom, all of a sudden you're in full-blown turbulence. So it's pretty awesome. And there's actually some researchers in Europe, I forget their names off the top of my head, but they actually created a pipe flow, because pipes are actually always stable to infinitesimal. You actually have a real disturbance in a pipe. But they would create a flow rate, this laminar, and pristine and in a basement and on magnetic levitations, and it would be completely laminar, and you could come up and like flick the pipe, and that would be enough disturbance to then boom, immediately push the whole thing into turbulence. So some really cool stuff. But what's fun here is, again, there are mathematical tools and solutions to these equations that show up and forms that have the transition. And so in Panton, they actually talk through, there's all of these different transitions later. Any good turbulence book is going to talk through sort of all the different transition paths. If you're like on an aircraft, you're going to have some of these three-dimensional things, like you have vortices coming off of a wing and things like that. So there's all sorts of transition paths that can happen. In some cases, you may want to delay transition to turbulence. In other cases, like flow of a golf ball, you actually want to increase turbulence to sort of get drag to go down. Okay, and so really, I think I've got maybe one more picture here. No, I don't. Okay, the really important part here is that what it actually takes in this equation, in order for there to be an instability, it actually always takes, I'll draw it here, it actually always takes a kink in the profile. Okay, this would be, the velocity of the boundary layer. It always takes a kink. Okay, well, basically where the second derivative is equal to 0. It always takes a kink, and that's the thing that kicks loose. And so that's, as an adverse pressure gradient comes up, it is going to form that kink. Okay, and so that's kind of the key part to it. So, like I said, this is just a flavor. Panton does a good job here, kind of giving you against the math like he's always done. It gives you a flavor of it. And so, yes, transition is actually a big research topic in academia. Transition is actually one of the hardest things to predict. So even from a real world point of view, like if this is actually an airplane or like an airfoil, predicting that can be pretty challenging. And there's actually companies out there that are trying to build a full laminar aircraft, and so for them, we've actually been suppressing all this. So there's really the world of applications here is pretty broad in the world of stability and transition. And again, that's why I like teaching this sort of, including in the thermodynamics undergraduate fluids, just to give that broad exposure to fluid mechanics. Again, otherwise I feel like students leave this idea of fluid mechanics of it's solved or it's easy or any of this stuff, and then the answer is like, no, it's actually rich and it's really, really hard in many areas. So so that kind of wraps up really the fluid mechanics portion in Panton. So you can go read You can go read a few more chapters. Actually, I think I hit it. No, chapter 26 is Turbulence, and then chapter 27 is Compressible. So I've actually already covered those before, so that really kind of concludes Panton. So it's a good book. And so what I'm going to finish with now is just kind of the sort of final piece here is back to statistical mechanics. Now, in this book club, I did bring a lot of the statistical mechanics stuff in earlier. And as you remember, when I was doing that, I was saying, hey, some of this is really for physicists. You're starting at the quantum level, you're sort of building it up because you already have a foundation in quantum mechanics. And then where you're wanting to go in the world of physics is going to be into the world of like cryogenics or, like helium-3 or there's all these, magnets and all these transitions. So, so if you are a physicist, then absolutely go do it. I'm really teaching this from an engineering point of view. And so I'm going to kind of just do the final highlight here. Okay, so to focus on it, so chapters 1 through 5, we already kind of covered, right? And so as you're reading it, focus on the mechanical engineering, right? So focus on engineering, but you can take a look at some of the physics. When you get into chapter 6, this is one part I want to highlight. So in chapter 6, you're going to take a look at, honestly, these are all like temperatures over some sort of transition temperature. And really, this is sort of degrees of freedom as you get warmer. If you think of a molecule, okay, and you have just a molecule, and at first, what's going to happen is you're going to enact the vibration modes. And this is a specific heat, by the way. You're going to enact vibration, and then eventually you're going to enact rotation. Okay? And so where those things occur, it depends on the molecule. So it depends, if it's helium, depends if it's hydrogen, oxygen, what have you. And really the degrees that this sort of happens, usually this unlocks, say, like around 1,000 or 100 Kelvin. So that's pretty cold, okay? Those are barely above the kind of the cryogenic worlds. And then the vibration, this is, depending on the molecule, can be about 1,000 Kelvin. So depending where you are, yeah, you will end up having some different portions of specific heat that jump in. And so it's worth reading here to see what are the mechanics of this. Again, as in engineering, we might just be like, here's a CV, go look it up, or I guess a specific heat. It is nice to actually see like what is happening between these. Okay, and then let's see what else is in there. Chapter 7. You have some Bose gases, and then chapter 8 is sort of Fermi gases. Bose are ones that can have the same state, so that's where you get like Bose-Einstein condensate. That's actually pretty wild stuff. So it's fun to go see some of that stuff. Fermi is where you can't actually. The thing that comes is really interesting here when you read over the Fermi gas. Actually, electrons in a metal can really well be framed as just like a gas in a bottle. It's actually pretty crazy because in a metal they can kind of move around and they collide and they interact and all stuff. So that one's really sort of interesting to go look at. Chapter 9 is into the early universe. So I'm not going to cover that here. It's a very interesting subject, but you can go take a look at that. What it says from thermodynamics point of view. Okay. Coming back to the engineering world, chapter 10 is actually really interesting where you depart from ideal gas. Okay, I have seen this taught in some sort of engineering thermodynamics texts, but not a ton. They might just kind of talk about it. At least here you're deriving it a little bit more. But one is the Leonard-Jones potential. Leonard-Jones potential. And basically, it is modeling the effect between two different molecules, as I was kind of drawing this up. Okay, and this is pretty important for some of those interactions. I'll just write it down: sigma over r to the 12th minus sigma over r. I think that's the 6th. Okay, so it's the potential between molecules, and this does have some deviation. Really in the engineering world, especially with today's computers, there's no reason to not actually call up thermodynamics functions, whether it's refprof, or I use a Python one called coolprof. That's open source. So there's There's really no reason not to actually look up your thermodynamic states. You don't have to do these things that we used to do in the past where you're making assumptions on constant specific heats and then hoping you're right. Especially in the world, like when I'm playing the world of rocketry and things like that. You get to higher pressures, higher temperatures, all of this stuff is going to have deviations from ideal gas. Okay? And then van der Waals forces. Van der Waals. Okay, these are all of these kind of intermolecular forces that come into play. So, worth reading it for sure. Okay, chapter 11. Let's again kind of bosons and fermions. So, as an engineer, you don't have to do too much. Chapter 12 is actually pretty cool on phase transitions. And so, we're used to thinking about phase transitions as just like solids to liquids to gas, and they are. But there's actually more fundamental theory here in phase transitions. And they actually talk about it like you can show magnets and all these different things. Phase transitions are pretty broader. In fact, if you get into the world of materials, okay, so materials have all sorts of phases, and different crystallines can form, and different. Just go look at the phase diagram for like a stainless steel or something. It's pretty crazy, okay. And so this is actually a broader discussion of phase transitions that would include all of those things. So if you're into materials, that would be a good one to read. Not too bad. And then chapter 13 is actually the Ising model of that. So kind of magnets and things like that. But very, very, very simple way to do phase transitions, and actually you can get a lot out of these Ising models. In fact, one of these models actually formed some of the earlier like machine language, machine learning type of a thing. So pretty neat algorithms there. Okay, 14 is a renormalization. Okay, that's a technique used very often in the world of physics. So unless you're getting to like particle physics and things like that, you don't necessarily have to get into that. But it's kind of like in Panton showing all the different math. That's one of those math that's going to be very useful going forward for a physicist. And then chapter 16 is actually like Monte Carlo. It talks about that. That's how you use computers to go solve a whole bunch of this. I'm sorry, my orange here is fading. Monte Carlo, chapter 16. And then actually 15, where I wanted to finish here with non-equilibrium. Now, this one I'm going to highlight over here. And so non-equilibrium is actually interesting because this is where lasers come from. So I'm going to finish that here with lasers. All right? So non-equilibrium thermodynamics is one of the ways that a chemical laser works. You actually have a chemical reaction like a rocket engine, effectively. And then you quickly make that rocket engine go supersonic. A lot of those molecules are actually now frozen in a higher energy state, but they're not colliding as much because you're now supersonic and kind of pressure is down. And so these chemical lasers actually do that. It's a converging diverging nozzle, and then you can seed it, and then you actually get stimulated emission. All of these molecules then start lining up and letting go. So like things like CO2 lasers and things like that. It's pretty cool stuff. So non-equilibrium physics is kind of the start of that. There's all sorts of things in the world of non-equilibrium physics, like in plasma physics for sure. You have situations where you haven't hit equilibrium. So really, that's kind of it. So this has been almost 30 episodes worth of thermal fluids. So we started off really in thermomechanics on an undergraduate level. We quickly pulled in some of the fluid mechanics so we could kind of finish off with conservation of momentum. It's not just mass and energy. We're in thermodynamics. You pull in fluid mechanics, it actually makes a lot of sense. We kind of came back and added some richness then in the fluid mechanics, back to thermodynamics, back to then graduate fluids, kind of finish up the whole fluids conversation in the thermal fluids, pulling from statistical mechanics where it makes sense, so that early on we have an idea of entropy, right? Again, you don't really have an idea of entropy without having touched statistical mechanics. And then there's the weird thing where we think we have an idea of temperature, but really don't. What you have an idea that human is actually heat flux, not temperature. They're related, but not that. And then we kind of got into turbulence and then really kind of the graduate like vorticity and different pieces along the way to give you that more insight and fluid instabilities and things like that, kind of finishing up here with transition to turbulence. We did a good couple lessons on turbulence. and then just sort of finishing up here with the statistical mechanics. A lot of that book that I read, it's a good book. I've read it. I do have a physics background as well, so I enjoyed reading this book. So please do go read through it. But from an engineering point of view, the ones that are important are sort of chapter 6, where you want to take a look at vibrations and rotations. It's a good description. And then come back with sort of the departure of ideal gas in chapters 10. And then maybe a little chapter 15, non-equilibrium, if you want to kind of take a look at lasers. So that's it for this book club on thermal fluids, and we'll see you for the next one. Thank you.